Welcome back to the Explainer. Whether you're totally gearing up for the IIT JEE or, you're just a focused learner who really wants to decode how the universe actually moves, you are absolutely in the right place. Today, we're putting together a super structured, totally foundational review of linear motion kinematics. I absolutely love this topic because it's all about finding order in the chaos of movement. We're going to strip away all the confusion and build a crystal clear, logical understanding right from the ground up. Let's get into it. Now, before we even touch the math, I've got to ask you something. Are you actually sitting still right now? I mean, you probably feel like you're at rest, just staring at this screen, right? But relative to the center of the Earth, you are literally rotating at hundreds of miles per hour. And relative to the sun, you're hurtling through space at tens of thousands of miles per hour. It completely blows your mind when you think about it, but it beautifully challenges our whole perception of rest. And it sets up the absolute, undeniable necessity of having a starting perspective before we can ever even attempt to measure motion. Okay, so here's our logical 5-step roadmap for today that's going to form an unbreakable foundation for you. We'll be hitting 1. Establishing your reference frame. 2. Speed versus velocity. 3. Acceleration, the changing pace. 4. Graphing the journey. And 5. The relative velocity puzzle. All right, let's jump straight into part 1, establishing your reference frame. We've got to start from the absolute ground up here. Why? Because you simply cannot track movement without knowing exactly where you're watching it from. Think of a frame of reference like your own personal set of X, Y, and Z axes, firmly planted in the ground, or, on a moving train. Honestly, whenever an IIT JEE problem asks you to calculate motion, your very first non-negotiable step is to establish this frame. Without it, your distances and directions are just meaningless numbers floating in space. Moving right along to section 2, speed versus velocity. Now, this is the exact spot where a ton of test takers get completely tripped up by subtle semantics. Look, speed is just a scalar quantity. It's kind of like a blindfolded runner on a treadmill. You're moving fast, your legs are pumping, you're racking up distance, but you don't have a care in the world about where you actually end up. That's magnitude only. Velocity, on the other hand, is a vector. It demands a destination. It's that same runner, but sprinting with absolute purpose toward a specific finish line. You've got the magnitude from the speed, plus that absolute critical element of direction. So let's say our sprinting runner locks in that exact same pace, covering the exact same distance every single second and stays in a perfectly straight line. That is what we call uniform motion. It is beautifully predictable. But notice the catch here. If their speed changes even a tiny bit, or they veer off that straight line, boom, it immediately becomes non-uniform motion. To actually solve complex kinematics problems, you have to be able to isolate these two ideas in your head. Average speed looks at the entire trip, right? It's just total distance over total time. It really doesn't care if you stopped for coffee halfway through. Instantaneous velocity, however, is a snapshot. It is exactly what your car's speedometer reads, combined with your compass heading at one singular, frozen moment in time. Mixing these two up is a classic trap on exams, so always stop and ask yourself, are they asking for the whole journey or just a snapshot? Let's kick it up a notch with section 3, acceleration, the changing pace. So what happens when that instantaneous velocity isn't staying uniform? A lot of folks hear the word acceleration and instantly just think, oh, going super fast. But scientifically, acceleration isn't simply going fast. It's the physical act of changing that speedometer's needle up or down. If you mash the gas pedal, you're accelerating positively. But if you slam on the brakes, guess what? You are still accelerating, just in the negative direction. You're slowing down that velocity. It's all about the rate of change. Now, when your foot on that gas pedal applies a perfectly steady, unwavering pressure, we get uniformly accelerated motion. This means for every single second that ticks by, your velocity ticks up or down by the exact same amount. It is incredibly consistent. And it's exactly because of that consistency that physicists were able to derive some pretty sweet, predictable mathematical rules for it. And here, they are the fruits of that consistency. These specific mathematical relations, which you probably know as the kinematic equations, become your absolute ultimate detective toolkit for the IIT JEE. They let you connect initial velocity, final velocity, acceleration, time, and displacement like puzzle pieces. But, and this is a huge but, remember the golden rule. These relations literally only work if the acceleration is strictly uniform. The second that acceleration starts fluctuating, you've got to leave this toolkit in the dust and break out the calculus instead. Which brings us nicely to Section 4, Graphing the Journey. Let's actually translate all those formulas into a really compelling visual story. Imagine this perfectly relatable journey for a second. A train pulls out of a station, right? Getting faster and faster. Then it hits top speed and just cruises comfortably across the countryside. Finally, it smoothly brakes to a complete dead stop at the next station. Let's watch how that exact same physical sequence looks completely different depending on the specific data we choose to look at. First step, look at a position time graph. Because the train is covering way more distance every second as it speeds out of the station, the acceleration looks like this upward bending curve. Then, when it hits that cruising speed, our uniform motion, that curve straightens right out into a crisp, diagonal line climbing upwards. It's moving, but at a constant rate. Then, as it finally brakes, the line curves flat, showing the position is just straight up, no longer changing. But flip over to a velocity time graph, and the whole visual story changes. That exact same cruising train, which is moving super fast but at a constant speed, now becomes a perfectly flat horizontal line. Why? Well, because the velocity isn't changing, so the line doesn't move up or down the y-axis at all. The initial acceleration out of the station is a straight upward slope, and the braking section is just a straight downward slope back to zero. Getting really good at reading these slopes correctly is just a massive advantage when solving physics problems. All right, the final piece of the puzzle. Section 5, the relative velocity puzzle. This part literally brings everything full circle, back to our original observer. Remember the very first thing we talked about today? The frame of reference? Well, everything we've mapped so far, the speed, the acceleration, all those graphs, it all changes entirely if the person holding the stopwatch happens to be running too. Relative velocity is simply how fast something appears to be moving from your specific and potentially moving point of view. It's wild how this actually organizes the chaos. Object C's motion is going to be completely, wildly different depending entirely on whether observer A, who's just chillin', standing still, or observer B, who's moving to the right, is the one doing the math. Think about it. If you're in a car on the highway doing 60 miles per hour and a car passes you doing 65, to you, they don't look like they're going 65. They only look like they're crawling ahead of you at 5 miles per hour. That right there is relative velocity in action. So as we wrap up our explainer today, I'm going to leave you with a really provocative thought to test out your new intuitive grasp of relative velocity. If you are running forward at 10 meters per second and you throw a ball forward at 10 meters per second relative to you, how fast is that ball moving to someone who is standing completely still on the sidelines? Really think about your frame of reference. Think about your vectors. Hold on to that answer and take that mindset with you as you crush those practice exams. Keep analyzing the world around you guys, and happy studying.
Welcome to the Explainer. Today, we're bringing that high-performance energy to break down the exact principles you need to absolutely conquer the IIT JEE physics section. We're diving deep into planar kinematics. Now, it's a fierce exam, we all know that, but we're going to see how shifting your perspective turns these intimidating hurdles into your ultimate playbook for success. Let's get into it.
Before we even think about those nitty-gritty formulas or complex diagrams, we really have to ask ourselves a crucial question. What truly separates a good physics student from a true IIT JEE champion? Is it just having a fancier calculator, or maybe memorizing a massive list of equations? Absolutely not. No way. It's entirely about how you visualize, deconstruct, and attack the problem. It's about taking this complex, multidimensional movement and breaking it right down into simple, manageable pieces.
All right, here is our tactical battle plan for today's explainer. First, cracking IIT JEE planar kinematics. Second, mastering motion in a plane. Third, analyzing projectile motion. Fourth, decoding uniform circular motion. And finally, your IIT JEE winning strategy.
Let's kick things off with Section 1, cracking IIT JEE planar kinematics.
The goal here is to transform the immense difficulty of the IIT JEE into easily digestible, conquerable building blocks. Look, the IIT JEE is a beast of an exam. There's just no denying that. The stakes are incredibly high. But by treating planar kinematics as specialized weapons in your arsenal, victory actually becomes a matter of strict methodology rather than just raw brainpower. You take the core concepts, motion in a plane, projectile motion, circular motion, and you build your foundation block by block until absolutely nothing can knock you down.
Moving right along to Section 2,
Mastering motion in a plane.
So, ocean in a plane. Think of this as the fundamental 2D arena where your kinematic principles are operating across multiple axes simultaneously. And here's a mind-bending fact that illustrates this perfectly. If you fire a bullet perfectly horizontally from a gun, and at the exact same time drop a bullet from your hand at that exact same height, they hit the ground at the exact same moment. Crazy, right? Why does that happen? Because what happens on the x-axis stays on the x-axis, and what happens on the y-axis stays on the y-axis. They are completely independent. Mathematically, the literal only variable linking these two distinct dimensions is time. Grasping that time is the sole bridge between your axes, well, that is your first major key to mastering this subject.
And really, making that jump from 1D linear motion to 2D planar motion is exactly where the IITJEE tests your true understanding. In 1D, like on that standard high school track, you really only have to worry about moving forwards or backwards. Pretty simple. But in 2D planar motion, you aren't just looking at a straight line anymore. You are simultaneously tracking horizontal displacement and vertical acceleration all on a grid. Transitioning your mindset from a single flat line to a complex coordinate plane is absolutely essential for this exam.
Now that the arena is set, we advance to Section 3, Analyzing Projectile Motion. Think about the arc of attack. We're visualizing the physics of a launched rocket here. See, what's really interesting is that we aren't just looking at dry, abstract math on a page. We are looking at the exact parabolic trajectory of a launched rocket, a thrown baseball, or even a leaping athlete. It's real-world stuff. If you can clearly visualize that perfect arc in your mind's eye, you can conquer the math behind it. You got to see the physics happening in the real world before you even think about plugging in those numbers. When the IITJEE tests you on this, you've got to break the flight down into 3 tactical, non-negotiable steps. Step 1, the launch. This is completely dictated by your initial velocity and your angle of attack. Step 2, the peak. Now watch out because this is a classic trap. This is the exact moment where your vertical velocity hits absolute zero. But remember, the object is still moving horizontally across the sky. Don't let him trick you there. And finally, step 3, the landing, which gives you your total range. If you master these 3 distinct phases and isolate them in your mind, literally no projectile question can trip you up. Our final act takes us into the endless loop. Section 4, Decoding Uniform Circular Motion. I want you to visualize a satellite in a perfect continuous orbit. Don't just picture some tiny object spinning on a string on your classroom desk. No, to get to that true champion level of understanding, you need to frame this physics concept in your mind as a massive satellite, perfectly locked in orbit around the Earth. Imagining the sheer, massive scale of that continuous loop really helps you appreciate the incredible invisible forces at play that keep that satellite from just flying off into deep space. Now, there are some rapid-fire constants and variables in uniform circular motion that consistently trip up unprepared students. So let's break them down. First up, constant speed. The actual magnitude of how fast the object is moving, that isn't changing. Second, changing velocity. Wait, actually, hold on a second. How can speed be constant but velocity changes? Well, it's because velocity includes direction, and in a circle, the direction is continuously, endlessly changing. And third, centripetal acceleration. That's the crucial inward pulling force keeping the whole system tethered together. Memorize this exact breakdown, guys. It is the absolute core of almost every single circular motion question they're going to throw at you.
Having mastered the plane, the projectile, and the circle, let's synthesize our game plan in Section 5. Your IITJEE winning strategy.
When we talk about the principles of planar kinematics, we aren't just blindly memorizing equations to regurgitate on test day. Far from it. By deeply internalizing motion in a plane, those projectile arcs and circular loops directly from the source text, you are arming yourself with the ultimate foundational roadmap. You aren't just doing math. You are fundamentally understanding the geometry of motion itself. You're learning to fluently read the language of physics.
So, we wrap up this explainer with a critical question for you. How are you going to deploy these fundamental planar kinematic principles to absolutely dominate your next exam? I'm challenging you, right here, right now, to take this tactical breakdown and apply it fiercely to your everyday studies. Because mastering these core basics, actually seeing the rocket's arc, feeling the satellite's continuous orbit, completely separating the X and Y axes in your head, that is exactly how you win the war and conquer the IITJEE. Keep studying hard, keep visualizing the physics all around you, and I will catch you in the next explainer.